Welcome to this module on the basics of remote sensing. A question that often arises in our mind is, why do we require remotely sensed data? Now, when we do a lab experiment or when we go to a place and make an in situ measurement, we are actually touching the medium. In remote sensing, the observation is being done remotely from a distance, and this actually provides a very different kind of perspective on things when you are part of your medium, you are part of your experiment, you're part of the experience. On the other hand, in case of remote sensing, the experience is a very different one when you are removed from the medium, when you are looking from space, when you are looking, say, about 400 to 500 miles away, or in some cases, even 30,000 miles away. So if we stand in a place and look at it, say in this case, the fruit in a tree, and we can zoom out, and all of a sudden, it takes on a new meaning. The trees are part of the broader system that sits on a landmass, that is a country, that's part of a continent that sits in the ocean. And as we step back further and further and look at those same trees, we may not be able to see the leaves from far away, but we see the trees and how they fit into the broader system, the clouds that surround them, the ice that is in its north or south, the oceans that are really affecting the climate that is causing those trees to grow. So these satellites are really the best way to measure the effects of climate change, because just one person on the ground in one place, it is very difficult to say what you see in front of you is due to climate change or due to some local phenomena, or it's just the weather. But from space, we can look at the whole Earth and we can integrate these observations of the Earth and really make a better assessment of what's causing these changes and what their long-term prediction might be. So in remote sensing, the process involves an interaction between the incident radiation and the targets of interest. The first step in remote sensing is to have an energy source which illuminates or provides electromagnetic energy to the target of interest. Now, as the energy travels from its source to the target, it will come in contact with and interact with the atmosphere it passes through. Now, this interaction may take place a second time as the energy travels from the target to the sensor. Once the energy makes its way to the target through the atmosphere, it interacts with the target depending on the properties of both the target and the radiation. Now, after the energy has been scattered or emitted from the target, we require a sensor, which is remote, that is not in contact with the target, to collect and record the electromagnetic radiation. The energy recorded by the sensor has to be transmitted, often in electronic form, to a receiving and processing station where the data is processed into an image. The processed image is interpreted visually or digitally or electronically to extract information about the target that was illuminated. The final element of the remote sensing process is achieved when we apply the information we have been able to extract from the imagery about the target in order to better understand or reveal some new information or assist in solving a particular problem. Now, however, in remote sensing, it also involves the sensing of emitted energy and the use of non-imaging sensors as well. Now, remote sensing involves the measurement of energy in many parts of the electromagnetic spectrum. The major regions of interest in satellite sensing are the visible light, reflected and emitted infrared, as well as the microwave regions. The measurement of this radiation takes place in what are known as spectral bands. A spectral band is defined as a discrete interval of the electromagnetic spectrum. For example, the wavelength range of 720 nanometers to 730 nanometers is one spectral band in this figure. So satellite sensors have been designed to measure responses within these spectral bands or within a particular spectral band to enable the discrimination of the major Earth surface materials. The scientists or researchers will choose a particular spectral band for data collection depending on what they wish to examine. So here we see a multispectral image and hyperspectral image. In case of multispectral images, the sensors interpret or intercept images in bands that are more than 3, more than 1 in number. And in case of hyperspectral images, the number of bands exceed 100, so up to hundreds of bands. So there are different sensors that are multispectral and hyperspectral in nature, and we will be discussing them in the subsequent modules. Now, the fundamental question in remote sensing is, how do we infer the information about the landscape from a set of measurements that constitute an image? The answer to this question is digital image processing. Now, this technique helps to manipulate and analyze the image data produced by the remote sensors in such a way as to reveal information that may not be immediately recognizable in its original form. So, remote sensing derived data may be transferred into information using these image processing techniques. Now, there are standard procedures that are used to extract useful information from the remotely sensed data. Now, these procedures include stating of the problem, collection of data, performing analysis of the data, presenting the information so that decisions can be made on the data that has already been processed. So in the subsequent modules, we will be discussing the steps involved in the remote sensing process. So we have 2 questions for you related to this module. The first question: of our 5 senses, that is vision, hearing, taste, smell, feel, 3 may be forms of remote sensing where the source of information is at a distance. The other 2 rely on direct contact with the source of information. Which are they? The second question: can remote sensing make use of anything other than electromagnetic radiation? Think about it. Thank you.